It's a pretty intimate space. Feel free to pop up with questions. Just to clarify, this is a technical talk. It's about data privacy. I know there was a question earlier about am I going to talk about GDPR. Not a lawyer. Anything about that. But not. So I think one of the things that's been really fascinating lately is watching how much has happened in the past year and how is that going to impact some of the technologies and some of the architectures of what we're going to be building in the future. So here in this talk, I'm going to be giving you a little bit of a snack-bite pieces of some of the latest in secure computing, data privacy, and how we can do a better job at protecting user data. And at Oasis Labs, we're building some technology, and I'd love to show you some of the things that we're doing to help you as developers and entrepreneurs to more easily build privacy-preserving and secure applications in the future. So this should be obvious to all of you. The world is run by data. There is so much data at stake today, and it's undeniable the importance of data in the modern economy. It affects nearly all aspects of our lives. The cliche is that data is the new oil, right? But the question is, are we doing it responsibly? I think there's a number of really deep technical challenges that come with how we are doing things today. And that goes every layer of the stack, from how users interact with data and our applications to all the way to the back end and how we manage data in our cloud and in our data centers. So there's a number of problems with how we do it today. I'll list off a few, which should ring true to most of you. Data breaches are a very frequent occurrence. This is one of those scary graphs. There's another one that's equivalent, which is a question of how often data breaches are happening every year. But this is affecting everybody. Data breaches are affecting governments, they're affecting large companies, they're affecting small startups. And it's really startling just how much data is being leaked today. So one of the things that that really drives us as a company is enterprises, on the one hand, are feeling like they're losing control of that data, partially because the security requirements of building secure, robust applications is getting harder, especially as adversaries are getting more sophisticated. To compound on that, there is an increasing feeling that users are also losing control of their data, and they're losing trust in the companies that are stewards of their data, not just because of data breaches, but we're increasingly hearing stories about how data is being used in ways that users may not necessarily approve of. And there's some pretty interesting stats. Recently, there's been some surveys where 63% of Facebook users have said that they don't trust Facebook at all, or not very much with handling information. And it's really interesting that about 50% of the folks that have quit Facebook recently actually cite explicitly lack of trust as one of the core reasons why they're deciding to delete that app and move on. And these problems permeate throughout our society. And one of the areas where we're starting to see a lot more pickup is that regulators are becoming more sophisticated. They're starting to understand some of these challenges a little bit better. It's going to be an evolving process. So obviously the regulations that are being proposed now are not perfect, but an increasing number of states are actually starting to propose a set of regulations that would address some of the data privacy problems that we see today. And there have been a number of proposals as well on the federal level. Not to be all doom and gloom, but I think there's an opportunity here too, in terms of if we are better capable of protecting the privacy of the data that we're stewards of the applications that we're building. I think there's a great opportunity here to be able to enable new applications to be built. And so here are a couple stats that I think kind of highlight that. So today, access is very often cited by data analysts and data scientists as one of the obstacles to being able to provide more interesting data insights and more interesting data analytics. Now, if you take a look at the average healthcare provider, the average healthcare provider uses 16 different EMR systems. The average Fortune 500 company uses over 500 different applications on average. All of you guys, I'm sure, can think to what types of web applications your company relies on. There are huge data lakes that are completely isolated from each other. And think about all the different things that we could do if we could pool that data together and enable new types of analytics, new types of insights that cross the gamut of sales and technology and ops and HR. So at Oasis Labs, our mission is to empower organizations to utilize user data in secure, compliant, and responsible ways. And there's three fundamental problems that we're trying to address. The first of which is that of untrusted infrastructure. And this might be a misnomer. It's not necessarily the case that you don't trust the cloud provider that you're building on top of, but it's impossible to say with 100% certainty that hackers won't get into your core infrastructure. So even in the case where hackers gain control of your infrastructure, even if it's the case that your password for your root cloud infrastructure has been phished from your sysadmin, we want to provide much stronger guarantees in terms of how your application is running, both confidentiality and in terms of the integrity of your application. Second of all, applications today, for the most part, operate over raw data. It's very common today through TLS that you'll see data being encrypted in transit. It's more and more common now that you'll start to see data being encrypted at rest. But more often than not, your applications are still operating over unencrypted data. And so compromise of the application trivially leads to a data breach. The third problem is that the results themselves often leak more sensitive data than you would expect. And this is sometimes accidental, sometimes on purpose, but more often than not, very frequently you'll see in the news that applications are accidentally leaking more information than you actually want. And so part of our goal here is to come up with a set of solutions that tries to address privacy and security at every layer of the stack. Now, we've reserved a ton of time for Q&A, so I'm happy to go into details, but I think at a high level here, there's so much content to go over. I'll give a quick overview of some of the components of the things that we're building to make this happen. To begin with, we have a new smart contract system. You can think of it as a blockchain protocol. The goal here is to provide much stronger guarantees and a much better performant system that can give you strong integrity guarantees and an immutable ledger of everything that's happening. We're doing a ton of work in the area of confidentiality, preserving smart contract execution. So the goal here is to build an application in an execution environment where we can encrypt the data, we can operate over that encrypted data in a way that even the operator, even the infrastructure, even the cloud provider, even the person plugging the device into the rack doesn't necessarily have the ability to read the unencrypted data of the application. And thirdly, we're working on a set of privacy-preserving algorithms, specifically for machine learning and analytics, where we can start to provide much stronger guarantees over what ultimately gets leaked out of any particular application. So with smart contracts are a really interesting abstraction. The goal for a smart contract is that we want to be able to provide a tool for developers where you may not be necessarily an expert in distributed systems, but if you put your application inside of a smart contract, you can think of it as a specific reproducible build piece of code. We want to provide really strong guarantees that the execution of that contract is executed correctly, and you can get a remote proof that the remote application, in this case, for example, something that you might be running in the cloud, is executing correctly with the correct result that you get back. Again, even if your cloud and your infrastructure may potentially be untrusted. We also want to be able to do this in a way that's relatively decentralized. So it doesn't require that you put 100% of your trust inside a single cloud provider. We want to decentralize this over a number of different parties such that even if any one of these are actively malicious, we can still provide end-to-end guarantees. And third of all, one of the things that you get that's really interesting is a really strong distributed ledger across these different entities, a record of everything that's ever happened in your system. So from an auditability perspective, it's fantastic. You can always go back and exactly trace everything that's ever happened on top of your smart contract with very high availability, integrity guarantees, and immutable data. Now, blockchains and smart contracts don't necessarily solve the confidentiality and the privacy problem. For that, we've been focusing on a number of different techniques for secure computing. Secure computing, for the technical folks in the room, involves a whole class of algorithms that involve trusted some of the examples that you may have heard of before are things like trusted hardware, secure multi-party computation, homomorphic encryption, zero-knowledge proofs. But it's a set of techniques where we can provide really strong guarantees in terms of the data that is being operated over. So, for example, in this case, if you want to encrypt your data, secure computing is basically the idea of being able to compute arbitrary functions and arbitrary applications over encrypted data. So it effectively emulates a black box for computations. Trusted execution environments are one example of this, where the data and the computation inside the black box can't be viewed by anybody. It enables computation over encrypted data without revealing the data. So as a developer, I would insert my program, I could give it encrypted data, and then I could get a result back with a strong proof that this program was executed correctly, and nobody outside of this black box was able to see the input data, which is a really interesting primitive. And third of all, there's a class of techniques that we've been working on, largely in the area of program rewriting and verification. And it basically boils down to the fact that everybody here, myself included, will write buggy code. And the code may not necessarily always provide the end-to-end policy that you actually want to enforce. So for example, you might want to provide a policy such that this data never actually gets reflected in this result in a way such that someone viewing that result would be able to get information about the underlying raw user data. So the goal here is to provide a verifier and a model checker such that with an arbitrary program and an arbitrary policy, we can provide formal proofs that the program can be automatically rewritten in a way that satisfies that particular policy. And one example of a policy that we've been focusing a good amount of time on is that of differential privacy. So if you're not familiar with differential privacy, there's a very long mathematical definition for this, but the high-level intuition is that if I have a particular query or a particular result that I want to get out of a particular database, if I execute that query with a differentially private algorithm, whether or not this database has Joe's data or doesn't have Joe's data, the result that I get back should be approximately the same or indistinguishable from each other. And what that means is that the outcome is the same with or without Joe's data. And a differentially private algorithm, if proven correct, should hold true for every user in every possible database that exists. And it's in short, one of the strongest definitions of privacy that you can think of, which is to say whether or not your data is in this or not, we can prove that the result would have been the same otherwise. Now, when you pair this with analytics and machine learning algorithms, we can start to build some really interesting systems, which I'm excited to show you next. So with these building blocks, the goal here is to provide a set of tools and a platform for you to build much more secure and much more private applications of the future. So in terms of each one of these components, just to summarize, the blockchain and smart contracts we use for policy enforcement. The guarantee that I want is if I upload my data into the smart contract, the only thing that will happen is this, the code that's embodied inside the smart contract, and I can get a remote proof that it was executed correctly. Not only do I have a remote proof that it was executed correctly, I have a strong immutable log of everything that's ever happened on that smart contract. And it's important because it allows us to do decentralized orchestration with really strong guarantees and much higher granularity of transparency. With secure computation and trusted execution environments, we want to protect the data and protect the computation inside these trusted execution environments such that it reduces the amount of trust that you give to machines or infrastructure providers to be able to properly manage the data. And with program rewriting and verification, we can guarantee that with an automated policy enforcer, it will eliminate the possibility that your program or your algorithm may accidentally leak data that it shouldn't. So let me give you an example of something that we've been working on and a set of abstractions that you could use as developers. So one way to think about what we've been building is that of high integrity secure serverless architecture. So in today's system, our status quo is that as a developer, I'm going to upload some code, some configuration into some cloud, and that's going to serve my application. And a user, either on a mobile device or a web browser, can interact with that application, push data to the cloud, or fetch results back. And the fundamental problem with this, that I'm sure is apparent, is that attackers who are able to compromise even a single cloud node often have a lot more power than they should. And in fact, if they are able to compromise an application server, very often they can completely control what gets returned back to clients and start snooping on the applications there. So in this particular example, an attacker who compromises an application server might be able to actually serve malware and snoop on what the users are doing instead of serving the application that was actually intended. So with our system, one of the things that we do is, as a decentralized system, we replicate across a whole number of different independent bodies. One of the configurations for this would be to operate in 3 completely separate clouds, for example. And in this case, by running a consensus algorithm across these 3 clouds and cross-validating the results and the state that gets generated from the execution of these computations, we can actually guarantee that even if one of these clouds was completely compromised, let's say you completely lost control and your root credentials have been taken over by some adversary. This consensus protocol can verify that the results that are coming out of this cloud are incorrect, and it can actually block and prevent these types of incorrect applications from being served to the user. So in this particular case, in this particular configuration, an attacker would actually have to compromise multiple clouds simultaneously in order to provide the effective ones. So one way that we've been looking into applying this idea is that of an infrastructure provider. So in one particular use case that we're working on with our partners, there is a cloud controller. This is a use case that they have where they're pushing code to a cloud controller, and that cloud controller is managing hundreds of thousands of either IoT or on-prem devices remotely. And as I mentioned earlier, the problem here is that you compromise this cloud server, and suddenly you can cause unexpected actions. A lot of times people use this cloud server to be able to push arbitrary actions to be performed by these nodes. So arbitrary malicious actors can now monitor information and maybe even erase information that should have been there. In our system, by replicating this computation in an immutable record across a number of different clouds, we can provide a much stronger guarantee of the integrity of the computations, the configurations that happen, and an immutable record of everything that's happening in this cloud controller to ensure that with stronger properties such that the infrastructure provider here has a much better idea of what's happening. And combined with secure computing and data confidentiality techniques, we can also make sure that the configurations themselves or the data that's being pushed to and from the cloud provider can also be kept private, even if, again, one of the clouds has been compromised. So that's one potential model that we've been using and exploring these types of applications. I'm going to go into detail of a specific use case that we've also been looking at with some of our partners, and that's of confidential data sharing. One of the things that's really interesting is once you start to pair together these different technologies, it opens up a new world, not just a more secure version of what we have already, but I believe it opens up new models and new business models to build things that we couldn't build before. And so let me give you an example of this. Today, when people share data, there's a lot of fundamental problems. In fact, I'm sure many of you, last time you've been to a hospital, have probably experienced this. Healthcare providers today have a pretty difficult challenge in securely sharing data between patient data between external partners. And very frequently, between the hospital and some data partner, what they'll actually just end up doing is requesting patient data and then manually sending either a fax or an email of a patient record that they've requested. And fundamentally, the challenge here is that the confidentiality of the data is dependent on these very manual human processes. There's no comprehensive view of the patient. You're just sending these PDFs back and forth. And there's no holistic way to take a look at the records that are being augmented and generated on both sides for a single patient. Enforcing access control policies is a serious challenge because you're mostly relying on legal agreements to make sure that people are, responsibly using the data in the way that they should. And there's almost no visibility once it's been fired off. Once you fired off that email, you have no idea whether or not they're using it in ways that you wouldn't have expected. So this data lifecycle is something that we've been putting a lot of thought into. And we've been trying to design smart contracts that help give this control to a set of users like the hospital. So in this particular case, in our system, we've been designing a set of smart contracts where a company, such as a hospital, might upload encrypted data and a policy attached to that to our platform. Similarly, data consumers, maybe one of the partners, can submit access requests, such as a program, to be run across that data, again, to our platform. Our program is automatically checked against this policy using the verification and rewriting techniques we're talking about. So, for example, one of the things that it can check for is, well, maybe these records should only ever be processed by an analytics program or a machine learning algorithm that satisfies differential privacy. So we can check for that automatically. The policy can then be, if it's satisfied, we can execute that in a secure enclave or a trusted execution environment to make sure that that data is handled properly. And then finally, this data access log is automatically uploaded to an immutable ledger so that there's no way that we can be accessing this data in a way that's not logged and not auditable. So compared to traditional solutions, sharing data right now is very difficult, it's very manual. Our goal here is to provide ways where the data is always encrypted and privacy techniques are used to protect against data leakage. Enforcing access control policies is a big challenge right now, mostly relying on manual processes. Instead, we use automatic verification and rewriting techniques to make sure that data policies are satisfied. There's little to no visibility right now on how patient data is utilized by external partners. In this case, we want to be able to audit everything that goes on in an immutable ledger. And we want to provide a comprehensive view of the patient such that instead of fragmenting the data across many different partners and disparate different cloud systems, we can have a smart contract that provides a holistic view of the patient data in one place. Now, one example of this that we've been working on with some of our partners at Stanford and at ATH is an application called Kara. And specifically focused on the medical data and medical research space. So in this particular application, we're trying to solve the problem of these siloed medical data silos by incentivizing doctors and patients to share research with each other and improve medical research. So in this particular demo, patients and doctors are quickly inputting data into a mobile app. To an application user, to a developer it's a little bit different in terms of how you develop these applications, but to a user, ideally it looks no different than any other application that you might build backed by a cloud, for example. The Kara application will automatically process that data and store it onto the Oasis platform. And then ultimately, Kara will automatically protect that user data using privacy-preserving smart contracts on the platform. So the outcome here is that patients can confidently choose when to share their data with stronger security and privacy guarantees. And medical researchers can use that data while still protecting the privacy on both ends. So we have a number of developer tools that we've released, and we encourage anybody here that might be interested in the platform to engage with us after this, but also check out any materials that we have online. We have a developer dashboard, which is an easy-to-use web page and web console where you can manage all of your projects, similar to what you would expect in a cloud console. We have public contracts that will help you get started if you've never written a contract before. And we have web-based wallets that streamlines the funding process and the crediting process so that you can easily get started with what are equivalent to cloud credits, but in this case, credits on the platform itself. We also have a gaming SDK, so for anybody that's interested in NFTs and tokenized games, we have a gaming framework that makes it very easy to build in-app game logic, which will automatically handle the network transport on game progressions, a web framework integration for being able to integrate with existing web tools like React, and a developer mode for debugging. So if you want to easily be able to figure out what's going wrong with your smart contracts. And easy to add confidentiality, which turns out to be really important if you want to build confidential games like poker or Battleship is another example that we have, where you want to make sure that your game state is kept confidential. We have built-in support for that. Other tools that we have announced and have publicly accessible are our privacy SDK, a robust set of libraries to make it easy to build confidential smart contracts. We currently have